Konstantin Luzyanin, Kostya, as most of you know him very well. He has joined CQE, our center, since a very long time ago. I have here some dates. For instance, he got his degree in 1980 in St. Petersburg State University with red diploma. You know that in Russia they have this red diploma when the student is exceptional with all marks, top marks during all the years, yeah. And so he got it in 2002, and then he joined our center during 10 years. He got his PhD here in 2007, and supervisors were, apart from myself, was also Professor Kukushkin, Vadim Kukushkin, from St. Petersburg State. He developed a very nice coordination chemistry on the activation of nitriles by coordination to palladium and platinum metal centers. And he got a few prizes. For instance, he was awarded Antonio Xavier Prize in 2008. I think this was the first year that this prize was awarded, so it was created as a recognition of the services that he developed on NMR. So research done on NMR spectroscopic methods. And all of you, or most of you, know him very well during all that period where he was manager with Professor Ascenso. He is not here at the moment, I think, but they were really controlling the NMR facilities that all of us benefited a lot. And he also got a prize from the Technical University of Lisbon, the Productivity Prize, Junior Research Prize. He got it in 2009 and 2010, 2 years. Then he stayed, he continued as a postdoc here, where he developed again coordination and organometallic chemistry along the lines that he had done, but with new projects. In fact, he was the principal researcher, the PI, yeah, of 2 projects, wasn't it? So that of the FCT. So this is a very rare case. We are complaining because we cannot have a project approved by FCT, but this man had 2. Okay, had 2. One and the other one just on the following year, I think, and so that was an exceptional case. Anyhow, after this, he joined Liverpool, where very interesting things were promised, but the reality was a bit different. Yeah, and then he left Liverpool and he went to St. Petersburg State University. But then Liverpool caught him again, invited him again because they were so happy. I regret that we cannot do the same as Liverpool did it. So during the time he was there, everybody liked him and his services. And then he was, well, called again, now with a new position, a better position, where he can have and develop his research group there. And I hope that things will go very well now. He continued to collaborate with our center, and I just mentioned you a couple of cases. He has been the supervisor or co-supervisor of 2 PhD students, Tatiana Nizimova, who has just finished the degree 1 month ago or so. She defended the thesis, and now Kostya is also co-supervising another PhD student, Rogério Shea, also here. And he is also collaborating with our PhD program on catalysis and sustainability. So today afternoon, all of you are invited, if you wish, to attend the lecture that you will be delivering within the homogeneous catalysis course, and so in the Katsu's PhD program. And apart from this is also special meaning because, as you know, our center is planning to celebrate the 40th years anniversary, and a number of initiatives are being planned. And this is one of them, and this is the first example, is really to use alumni, and so people who really collaborate and were members of our center who are no longer here, but in fact we take the opportunity when they visited us to deliver a lecture. And so this is the first one within the scheme. And so Kostya will open the series of lectures that will follow of alumni of our center. And so the title is this one that you see here, and we are looking forward to listening. Thank you, Kostya.
Well, I'm very happy to be the first example, and I would like to thank Professor Pombero and the organizing committee of the Chemforum for the very kind invitation to deliver this talk. As you have seen in the program, it is entitled as Aminocarbines in Catalysis Revisited, although the mechanism is important. And in the first part of this talk, I would like to focus your attention on the topic that some of you may say everything has been done since a long time ago. That I will try to convince that it is not yet. While in the second part, I would like to bring some information on a field where nothing is known, and I would like to convince you that we are first of the kind. So when we develop a new catalytic system or the new catalyst, there is a set of requirements that we try to fulfill. Obviously, there can be academic requirements, such as, for instance, publish or perish, if you wish, or there can be some industrial requirements that are typically expressed in euros or in British pounds. So, application of the new catalyst. It is not a secret that application of the new catalyst, in particular in industry, is hampered by several reasons, such as low efficiency, high catalyst loading, and the price of the catalyst. That's why it's not surprising that majority of the catalysts used in industry for cross-coupling reactions are still the classical complexes with triphenyl phosphines discovered nearly a century ago, or with simple and heterocyclic carbenes. For a long time, we've been considering the price of the metal at the catalyst core as the major contribution to the price of the catalyst, but this slide convinces you that it is not the case. Indeed, modern ancillary ligands that are used for catalytic reactions typically cost much more than the corresponding metals that are used to be bound to. Consequently, the development of this so-called ideal catalyst that should be affordable, efficient, and versatile is still a very important task. So there are several types of contemporary catalysts used for organometallic catalysis that are presented on these slides. The most common, the classical phosphine ligands. They are very reactive, but they are chemically and thermally unstable and also toxic and environmentally harmful. And heterocyclic carbenes, they are stable and efficient, but with some rare exceptions of very simple imidazolium-based carbenes, the synthetic access to them is severely limited, so it's difficult to perform a precise tuning of them. And finally, cyclic diaminocarbenes that emerged in the market approximately 10 years ago. They are structurally similar to heterocyclic carbenes without a backbone. So they possess nearly similar donor properties and heterocyclic carbenes, but also in a combination with the so-called rotational flexibility that allows them to adapt the catalyst core better to the different requirements of the catalytic steps. But the major advantages of these ligands and their catalyst on their basis is actually in the existence of several methods for their preparation, such as those presented on this slide. So here we have a direct complexation that starts from the available formamidinium precursors that are deprotonated in situ, followed by the coordination to the metal core. When we have the method that organic chemists like a lot, that is an oxidative addition, that starts from the nearly similar chloroamidinium precursors that are oxidatively added to the metal center in low oxidation state. Traditionally, palladium 0, platinum 0 salts are used. And finally, the method that we are interested in developing is a metal-mediated nucleophilic addition to isocyanide. So, as you can understand, this method presented here, it's versatile, efficient, and atom economic because it is an addition reaction, so it doesn't produce any waste. It starts from the widely available precursors such as isocyanides and nucleophiles that are commercially available, and that allows for the easy modification of the catalyst structure just by swapping or choosing the appropriate nucleophile and isocyanide pair. So here I summarize some of the most important features of this approach. So this route requires a metal center that can provide a sufficient electrophilic activation, such as typically late transition metal in high oxidation state, platinum to palladium gold free. So if I take a nucleophile, I can generate a corresponding diaminocarbene, a cyclic diaminocarbene. If I take a dipole, at the same time I can form heterocyclic carbene by the same route. So in the last 7 years, when we restarted this project in our group, we published approximately 40 papers on this topic, so obviously I have no time to talk about all of them. I've just selected few most impressive, from my perspective, results. So our first not very successful study was the addition of the imine to platinum-bound isocyanide. So it furnished a very unstable aminocarbene, but unfortunately we could not isolate it in a free state, so we were only able to characterize it in solution using quite complicated mass spectrometry and NMR techniques. So apparently this aminocarbene was very, very unstable, so we decided to improve its stability by using a heterocyclic imine. There are several examples that we published. Here you see an imine or isoindolinone, but we also have some diimino species and some other related compounds. So in this case, the nucleophilic addition produces bidentate carbene species that is stabilized naturally by the chelating effect. So we have many examples and some extra structures for these compounds. After this, well, as you probably noticed, the addition of the amine, that is typical sp3 and nucleophile, to isocyanide generate us the diaminocarbene species that, let's say, organic people like to say traditional or canonical representation of the diaminocarbene. So you have two equal CN bonds that are intermediate between single and double. So you have a delocalization of electron density here. This is a traditional diaminocarbene. While in this compound that we obtained from the addition of imines, we do not have such a delocalization. We have two distinct bonds, one is single and another is double. And there are many questions regarding if we can even call this compound as carbene. So to answer this question, they use a nucleophile that is presented here, that is a hydrazone, that the hybridization of this NH2 center depends on the substituents that we place here. So if we take something very bulky and electron withdrawing, such as, for instance, anthracinyl or phenanthroynyl ligands, the hybridization of these nucleophilic centers goes to the pure imine hybridization or sp2m hybridization, as in the heterocyclic imines. So if we take something small and electron donating, such as methyl, for instance, the hybridization increases to the pure amine sp3n state. So we take a series of hydrazones of different structures and they studied their reactions, and we were able to prepare the complexes with carbene in the classical form. Here you have the diphenyl hydrazone. Its structure is confirmed by X-ray diffraction, but by taking this bulky electron withdrawing hydrazone, we prepared the carbene in the other form, and its structure was also confirmed. So addition of two structurally related hydrazone furnished us two structurally distinct carbene ligands, so we can call them both as carbenes. So all the nucleophiles they studied before this point were monofunctional nucleophiles with one nucleophilic center. So we decided to take so-called polyfunctional or ambidentate nucleophiles. For instance, here you have an example for amidines. So there are two nucleophilic centers. Here is imine and amine. And in this particular case, we found out that the radioselectivity of the coupling depends strongly on the nature of the isocyanide. Indeed, if we take something aromatic, such as xylyl, the nucleophilic addition occurs by this imine function, while the secondary amine functionality coordinates to the metal center forming these chelate ligands, while in case of the aliphatic third-butyl isocyanide, reaction is reversed and the glyphilic attack occurs by the imine function. Well, surprisingly, if you take cycloaliphatic components, the reaction proceeds by both ways, so it loses the selectivity. Another nucleophile that we studied was an aminopyridine. So the addition of the aminopyridine to isocyanide was previously studied by Beluca in 70s and 80s. So he published the addition of the aminopyridine to an isocyanide, giving this chelated complex. So as you can see, in this complex there are two NH groups, and all these compounds can potentially play a role of a metallonucleophile. So if we take a fresh molecule of an isocyanide, we can tailor two of these metal center by two carbines. So we have one carbon ligand here that is generated through this reaction, so it's a bridging carbon ligand, while the second carbon ligand, we call it exocyclic, is generated during this coupling. So I would like to remember this complex. It will be very important in the second part of my talk. Well, organic chemists ask us to prepare some chiral cyclic diaminocarbon ligands for symmetric catalysis. That's what we did. So if you take an enantiamerically pure esters or amides of the amino acid, we can produce chiral cyclic diaminocarbon complexes of different metals, and the examples are presented on this slide. Surprisingly, only few distinct types of amino acid actually participate in this reaction, while all others give a huge mixture of products that cannot be separated. So all the well-defined complexes that we prefer, we verified the absolute configuration of the chiral center, and we observed that in all of these examples, it is retained in the course of the metal-mediated coupling. So, as I said to you at the beginning, from isocyanide we can also generate anheterocyclic carbines, and here I provided the example of the addition of nitrones to isocyanide. So this was the first example of the addition of alanine type dipole to isocyanide. So with a cyclic nitron we generated these very unstable carbene species, but when we used the heterocyclic imine, such as this pyrroline and oxide, the reaction furnishes quite stable compound, and its structure was also confirmed by the X-ray diffraction. Well, unfortunately, these compounds cannot be used in asymmetric catalysis because they are produced as racemic mixtures, of course. So now I would like to provide only few examples of catalytic applications among what we have. So one of the first systems we studied was a Sunagashira reaction. So our first application of these amidine-derived compounds, well, produced not very efficient system, as you can see. It has very limited scope. Nevertheless, it has quite low catalyst loading, can operate under mild conditions. So we learned from our study, we improved our system by using different type of carbines, and we, again, were able to develop the catalytic system that operates with a very low catalyst loading, guarantees us very high turnover numbers with some limited scope, but the best of this catalytic system, that with use of this catalyst, we were for the first time able to establish the full catalytic cycle for the cyclic diaminocarbon ligands. As you can see, with our diaminocarbon catalyst in hand, this is not a real catalyst, it is a pre-catalyst. So during the first step, there is a formation of the catalytically active species by the reduction of the metal center, followed by the removal of the chlorides. So we form this compound. Then there is an oxidative addition, is the first step of the cross-coupling reaction, forming this intermediate that we were able to detect by the high-resolution mass spectrometry. So there is then the pi coordination of an alkyne with the replacement of an isocyanide ligand. When we have back coordination of isocyanide and alkyne binding to the metal center, cis-to-trans isomerization, and we again were able to identify this isomer, followed by the reductive elimination that liberate our product and regenerate the catalyst. So we also undertook some additional studies with the classical mercury drop test, that is a test for nanoparticles form, and well, no nanoparticles was obviously formed, and there is no any induction period in this process, so the initial kinetic is linear. So it clearly states that the mechanism of this catalytic cycle is molecular. Okay, so during the catalytic cycle, we observe the formation of small palladium clusters that, as we found, are not catalytically competent, so they cannot catalyze this reaction. And we consider this as a catalyst, the activation pathway. One of the questions that is regularly asked, why do we need the second isocyanide in our complex? Well, in pursuit of this catalytic study, we actually rationalized the role of the isocyanide. You see, we took the same catalyst as here, but we replaced the isocyanide with different ligands, such as halogens or phosphines or some other carbon, and we found out that isocyanide actually play a role of the molecular clamp at this stage. It prevents the formation, the immature formation of the palladium clusters by the back coordination at this step. So isocyanide is required to guarantee those high to lower numbers and to lower frequencies. So the next, at this slide, I just extracted 4 most active catalytic systems for Kosovo-Gashura reaction based on the heterocyclic carbines from the literature. And as you can see from our system at the top, it possesses the largest number of benefits compared to the other reported examples. The second example that we studied is hydrocellulation of terminal alkynes. That is a widely used industrial process, and it is also a very good benchmark reaction for new catalyst and benchmark reaction for the hydrocellulation for the cross-linking of the silicon rubbers that is used commonly. So there are 2 widely employed catalysts. The first is known as Spire catalyst. The second is Karstedt catalyst. They all have advantages and disadvantages, but the major disadvantages of both of them that they are not versatile. So they operate on the only in a very narrow range of conditions for very specific substrates. With our catalyst in hand, we were able to establish the first example for the application of platinum, cyclic diaminocarbons, and the hydrocellulation of alkynes. This system possesses a very wide scope, and as you can see in this slide, again, the number of benefits compared to the other systems is much higher. And just to conclude this hydrocellulation topic, we also patented the system on basis on platinum hydrocellulation catalyst for the production of silicon rubbers. With some of these catalysts in hands, we also established the full catalytic cycle for this reaction. Well, some of you probably remember this mechanism. It's known as Chuck-Harrod mechanism of hydrocellulation. However, it was never established for heterocyclic and acyclic diaminocarbons. Again, we have a reduction of platinum center giving us these species. When we have an oxidative addition of hydrosilane, and this product of this addition is identified by high-resolution mass spectrometry. When we have a pi coordination of alkyne again, giving a mixture of 4 isomers. When we have isocyanide back binding and alkene insertion, and these intermediates were detected, followed by reduction elimination. The catalyst, the activation pathway is again accompanied by the production of the small platinum clusters. This is a molecular catalysis, as it is clear from the mercury drop test and initial kinetics evaluation. The last catalytic example in this part, these are 2 systems for Suzuki-Miyaura coupling. Well, the first system, that was actually our first paper on Suzuki catalysis in the group. So we developed a catalyst that guarantees us to lower number of more than 1 million. At that time, that was the most effective catalyst ever published in this field. So the second system, this is the first system on basis on acyclic diaminocarbons that operates in water in aqueous conditions, so it is compatible with functionalization of biomolecules. So in the first part of my talk, we were talking about the cross-coupling reaction that operate with a highly prefunctionalized substrate, such as those containing, for instance, polar C halogen bond. Obviously, from the fundamental point of view, and from the point of view of atom economy, it will be very important to functionalize it directly the CH bond. One of the main problems encountered in the functionalization of the CH bond is selectivity. For instance, if we talk about the functionalization of arenes, there are many aromatic CH bonds of nearly similar reactivity. So that's why we need a so-called directing group that will lead our reaction during the cyclometallation to the functionalization of the product in or at the required site, as presented on this scheme. So in our group, we are very, very interested in the functionalization of the sulfur-containing compounds, at least due to two reasons. The first, the fundamental reason, for many decades, sulfur-containing substrates were person non grata in catalysis because sulfur poisons catalysts. Well, we like challenges, so we would like to overcome this limitation by using sulfur-containing substrate. And there is a secondary reason. Well, there are many sulfur-containing compounds in industry. Here, for instance, you have free sulfur-containing pharmaceutical drugs, and the direct functionalization of the aromatic function in these drugs in the future represent a straightforward approach for the modification of these compounds that can prevent them going out of the market due to the loss of efficiency, for instance. So we've decided to study the alkynylation reaction as a starting process for the CH functionalization, and obviously before synthetic procedures we did our homework and we try to understand what is known in the field and how can we contribute to it. There are several reports on functionalization via CH activation of the organic substrate. Here you have two examples of the functionalization of azoles and thiophene. So what is obvious from both of these studies, that the role of the sulfur is not clear, and it is definitely not the directing group, and no binding of the sulfur moiety with palladium occurs during the catalytic process. In the development of this study, again the functionalization of thiophenes was undertaken. Here the authors produce mechanism that is most probably incomplete. This reaction requires a very strong oxidant that does not participate in this mechanism, and again sulfur does not play the role of the directing group. It doesn't affect the rate of this reaction. So the first two examples of the using of the sulfur moieties as a directing group was reported in 2012. So as you can see, thioethers were applied in this case. And the authors proposed this fantastic catalytic cycle that starts from palladium-2, followed by the cyclometallation of the substrate, forming this intermediate that the binding of the sulfur is obvious. When there is an insertion of the alkane in palladium-C bond, beta hydrogen elimination, giving our product, and then reoxidation of our catalyst core to give us palladium-2 species. So from this study, we can easily conclude that the sulfur is directing group. It doesn't block palladium catalyst. This mechanism is redox mechanism, and reaction follows typical organometallic pathway. In the development of this study, different directing group, this is a pyridyl sulfoxide, was used, and again it follows the organometallic route. However, the scope of the system was very limited, and in comparison to the previous example, no product for the corresponding thioether was obtained. So in order to proceed with our studies, first we aim to understand why the reaction conditions for the functionalization of different sulfur-containing substrates were different, and how we can compare these conditions and employ it in our studies. So what we did, here you see 7 sulfur-containing substrates that we prepared from the corresponding tiles. Here our model reaction, And then after many attempts playing with different solvents, different reaction conditions, different oxidants, different catalysts, we were able to find the set of conditions where all or nearly all of our substrate produce our target alkylation products. And actually, from the next two tables, you can clearly see that the conditions, the optimum conditions, include the use of the dual oxidant source, that is silver trifluoroacetate plus gaseous oxygen. So after these studies, we were able to establish the reactivity route for our components. Indeed, the most efficient directive group is a thioether group, followed by the pyridyl sulfoxide, the thiophenylpyridine, and then finally benzyl thiopyridine at the end. However, in the presence of the ethers, pyridyl ethers, this substrate stays in the middle of this row. Some substrates were absolutely unreactive, and there is a very simple explanation for this. For instance, first two do not contain aromatic function that can be functionalized, while the last two cannot cyclometallate due to the steric reasons. Okay, so an obvious question came to our head. If the reactivity is so different, what will happen if we take a mixture of several substrates? Okay, so this is very difficult and very large table containing all possible two-component mixtures from these 7 substrates. In all of these cases, the reaction occurred only at one substrate, so this reaction is substrate selective. So later on, we expanded the systems to 3, 4, and even 5 component mixtures of different substrates, and in all of these mixtures, only one substrate was a subject of the alkylation, as it is indicated in red color in this table. So therefore, what we can conclude from these preliminary studies that orthogonal substrate selective functionalization of a mixtures using CH activation is indeed possible. This is the first example of it. So in all of these reactions, most reactive component is converted first. Across all the sulfur-containing substrate, thioethers are the most active compounds. So before I proceed with the further story, I would like you to explain why do we need the functionalization of mixtures. You see, many of you probably know, but everything that is sulfur-containing that we use in our life comes from one unique source, that is crude oil. Crude oil contains a number of sulfur compounds, typically thiols, that are during the process that is known as hydrodesulfurizations, they are denatured and transformed into the hydrogen disulfide and then to elemental sulfur. When industry takes this sulfur and transform it back to one or the other compounds using typical organic reactions, of course. The alternative procedure to the hydrodesulfurization will include the selective functionalization of only one component in the starting mixture of thiols. So if we develop a procedure that allows us to take a sulfur-enriched fraction of oil and then selectively functionalize only one component in it, then we don't need a hydrosulfurization, and the nature of our starting product will stay intact in the course of this process. Obviously, we cannot directly functionalize thiols via CH functionalization because thiols kill the catalyst, obviously. So what we need to do, we need to perform in situ derivatization of thiol-enriched crude oil components using, for instance, bromopyridine that forms a number of pyridyl ethers. And when we did mixture, again, we undertook the olefination reaction, and in this case, still one component was only functionalized in this process. Okay, before I show this, when actually we started, when actually we took a crude oil and enriched it with some thiols to perform our reaction, we were surprised how fast our catalyst is degraded in the course of this process. Well, obviously there are some trace thiols always present that kill the catalyst. So, we thought about the development of the catalyst core that will be still binuclear. It will contain two palladium cores that will be tailored by some ligand that will prevent this palladium core to be poisoned by the tiles. And from our carbene studies, as you remember, we have a perfect example of this catalyst. We have two palladiums that are placed very close to each other. They can work in this reaction and they improve the selectivity of this process. From our preliminary studies of mechanism, here you have the kinetic curves. As you can see, the kinetics is not the primary factor that drives this reactivity difference. It most probably thermodynamics, or in other words, the selective binding of one substrate, preferential binding of one substrate to the metal curve. Before I conclude, I would like to say that in the last years we developed a number of catalysts, and we developed a method for their preparation and a method for the optimization of the carbene catalyst to every required application, as you can see, even including the modern ones. Well, finally, I would like to thank all the institutions that I worked in the last, 15 years, and of course, Centro de Química Estrutural, in the first place, that the isocyanide project originates from. St. Petersburg State University, several funding agencies, laboratory of cluster catalysis, many undergraduate and PhD students, collaborators, and these are the funding sources that I got in the last years, and finally the University of Liverpool for providing support for my current activities. Thank you very much for your kind attention.
Well, thank you very much. Very, very nice.
My pleasure.
Coordination organometallic chemistry. And so, comments and questions, please feel free. Well, perhaps I can start with. That is very rewarding to see all this beautiful chemistry on isocyanides that are activated towards nucleophilic attack by what we can call electron-poor metal centers. And this is particularly interesting because I studied my research with isocyanide chemistry in Sussex, and so I like a lot isocyanides, although they can be very, very smelly. But the type of chemistry was the opposite that Kosta has just shown. And so that project that I had was on the activation of isocyanide by very electron-rich metal centers, where the isocyanide was activated towards electrophilic attack. And here is really the opposite. So the same substrates, depending on the metal center, so they are activated in the opposite way, depending on the electronic properties of the sites, of the metal sites. So I'm very pleased to see all this beautiful chemistry that you are developing on isocyanides. And that's totally opposite the one that allowed me to initiate my research. So I think you see, that's the cycle of life. I started with isocyanides, and now. Okay, more questions, comments? The role of the isocyanide as a free species was also quite unusual, I think. Mm-hmm. Because you had the isocyanide as a ligand, and it came out. Mm. And I mean the Sonogashi type reaction. Yeah. And then the isocyanide free, not as a ligand, has also a fundamental role. Did you find that in other cases?
Well, we studied three reactions for now: Sonogashira, Suzuki, and hydrosylation. So in all of them, isocyanide is removed during the catalytic cycle, but then it is coordinated back in the next step. So, you see, we were very surprised to detect this decoordination of isocyanide, but we were very pleased to know that actually it is known from the nanoparticles research that isocyanides and carbenes, they are very bad ligands to form nanoparticles because they don't stabilize, they don't support the aggregation of nanoparticles. So that's mechanism that the isocyanide actually precludes this aggregation. Well, it's reasonable.
More comments? And the sulfur stuff, that is even worse than isocyanides.
Well, isocyanides, titles after isocyanides, they don't smell. You know?
Yeah, methyl isocyanide is very smelly, yeah, but it's very volatile. Not this one, but you know, study. Okay, well, if there are no further questions, well, Kostya will be lecturing, as I mentioned to you, this afternoon, and he still will be here for a couple of more days. And so I'm sure he will be pleased to talk to you if you wish. And, well, if there are no comments or questions, I think, well, I believe, I'm sure on behalf of all of us, of our center, well, we are very pleased.
Thank you.
I can say it again, we are very pleased to have you with us, although for a short period. And we all wish you the best of luck and highest success in your new position in Liverpool.
Thank you.
So we hope this collaboration will continue for many years. Thank you, Konstantin.
Thank you.